Hi everyone. So this is on section 2.6, the first half. So I'm going to cover the homogeneous differential equation, or really it's really the homogeneous f of xy. And this will allow us to convert something that is not separable into something that is separable, and it's through a substitution. So this is homogeneous if you can view f in two variable as f of a single variable, and that variable is y over x. So for example, here's a function in terms of y and x, which is simply y over x. But I can also view it as a single variable, so then if I call that y over x as v, this is simply v. Here's another example. Here's a function in two variables. So f of xy is y over x plus 3 times y over x squared. I can view this as a function of a single variable, and that single variable takes on the ratio of y over x. And I can view that as f of v, which is v plus 3v squared, where v is y over x. So this is what we call a homogeneous function. Another way to really define what a homogeneous function is, it contains a property that if you take that function and you scale it by a factor of t, the t will just cancel. Leaving you just the f of xy, then it is homogeneous. Later on, you'll see this definition used again for a different setting, and it's actually quite related through this property here. If you have a common factor, it will just you can cancel it out. Okay. Okay. So we're going to start with this differential equation, dy dx. And this is our standard variable. I can always switch it up by using x and t or any other variable I want. And you guys have to really be able to identify what is your dependent and what is your independent variable. So this is our beginning problem. It's not exact. It's not separable. But if f of xy is homogeneous, we can apply a substitution to make it separable. So given dy dx as f of xy, and we can view it as a function of y over x, we can let v be y over x, which means then v times x is y, or really y is v times x. Then if I differentiate the left with respect to x, differentiate the right side with respect to x. Now this is going to be a chain rule, because again v depends on x, so you can't just assume that it's a constant So not chain rule, product rule. So I'm going to keep v, differentiate this with respect to x. Well, that's a 1, right? Because we're differentiating with respect to x. So keep v, differentiate x with respect to x, you get a 1. Now I'm going to keep x, differentiate v with respect to x, is dv dx. So dy dx is v plus x dv dx. Now by applying the substitution, I get to view the right side as f of v, left side, while dy dx is going to be v plus x dv dx. And so moving the v over to the left side, you can see that this is separable. This here is all in terms of v. This is x dx. So I can separate the v to one side, separate the x to the other side, integrate with respect to x, integrate with respect to v, and you get yourself the solution. Very simple. Let's try a problem from section 2.6. So let me bring up a problem from section 2.6. Okay. So example. So this is number 11 from the book. You have y squared minus xy dx plus x squared dy is equal to 0. And you'll see how this is homogeneous right away. If I multiply everything by t's, it will just... So if I kind of replace y with yt, replace x with xt, you'll see that all the t's will just cancel out, because that'll be a common factor. So you can cancel both, all the t's on the left with just divide out all the t's and it'll just be gone. Okay, so it is quite related to this 0 right here as well. Okay, well, let me just go back to the definition I showed you guys earlier. If I move this dx term to the right side, and get dy dx by itself, you'll get this. And this is your capital F of xy right now. And I have to show that it's homogeneous, and it's going to be homogeneous. How do I do it? Well, you replace x with xt. So scale everything by t. So that'll be a tx, ty, ty, tx. And what do you notice? There's a t squared on top with t squared on the bottom. That will cancel out, leaving back to x and y, and that's exactly the original f of xy. So it is homogeneous. Right? Scaling both x and y by t does not affect the value. So this is a big hint. I can now write it in this form. So I can group everything so that all you see is just y divided by x. And that's going to be our plan. So what I'm going to do first, in order to get this to be y over x, I need to somehow divide by x squared. So I'm going to multiply both top and bottom by 1 over x squared. Or actually, I see an easier way. I'm just going to both divide each term on top and bottom by x squared. So it's xy divided by x squared. And you can see that it's y over x. There it is. This is your f of y divided by x. So I'm going to let v be y over x, which means that y is v of x, which means dy dx is v plus x dv dx. So now the right side is just v minus v squared, because that's v is. The left side, dy dx, is going to be v plus x dv dx. And so x dv dx, if I move that v over, it'll cancel out this v, so it's a minus v squared now. So dv divided by negative v squared is equal to dx divided by x. So we're ready to integrate both the left and right side. So the right side is simply natural log of x plus c. And the left side is 1 over v. And that's it. Well, we're not quite done. We start off with the differential equation in terms of x, y. Here are solutions in terms of vx. So one very last thing, I need to replace that v with y over x. So the solution here is going to be 1 over y over x, or really x over y. And to get that y by itself, and that's our general solution. Okay? All right, so that's it. Let me do another video on section 2.8 on the Bernoulli situation. I'll see you guys in the next video.